Hello class. In today's video we're going to go over example 22.1 on page 728 in our textbook. The example is electric flux through a disk. So the problem we are trying to solve is that we have a disk with a radius of 0.10 meters that is oriented with the n-hat vector at an angle of 30 degrees above the electric field. As you can see on the image on the bottom right, the electric field is pointing to the right, and the n-hat vector has an angle of 30 degrees, so the disk has that angle. We are given the magnitude of E, which is 2.0 times 10 to the third Newton coulombs, as well as the angle of 30 degrees between the n-hat vector and the E field. In part A, what we're looking for is we need to find what the electric flux is through the disk. So in order to begin a problem like this, the best way to start is to remember all of your equations and then write down everything that you have given. So what I have done on this page is I have the equation of electric flux, which is equal to the magnitude of the electric field dotted by the magnitude of area. So recall that we were already given the magnitude of the electric field, which was 2.0 times 10 to the third Newton coulombs. We don't have to do any conversions of that because that's already in standard form. We have the angle phi, which is equal to 30 degrees, which was the n-hat, the direction that it was, or the angle that it was rather, from the electric field. And then we have the radius of the disk, which is equal to 0.10 meters. The hardest part of the problem is probably determining the area, but recall that an area of a circle, or a flat disk rather, would be pi r squared. So that would be our area in this case for the magnitude of area. So with this specific problem, we actually have everything that we need in order to solve it right off the bat. The only hard thing was deriving the equation for the area, which in this case was pi r squared. And we have the radius, we have the electric field, and we also have an angle. Also recall that another way to express this vector equation in non-vector form is by just doing E times A cosine phi, and this will give you the final answer. The calculation on the final answer will be 2.0 times 10 to the third Newton coulombs times 0.0314 meters squared found from the equation pi r squared for the area times the angle cosine of 30 degrees, and our final answer ends up becoming 54 Newton meter squared coulombs, and that is our electric flux through the surface of a disk, and that finishes part A. So in part B in this question, it is pretty much asking you what would happen if the n-hat vector was at a 90-degree angle or perpendicular from the electric field. Recall the electric field was oriented in the rightward direction. What would happen if the n-hat vector was at a 90-degree angle? So to give you a visual representation of that, you can see that the disk is now at a flat, kind of flat, parallel with the E field, and the n-hat vector is pointing with a 90-degree angle away from, it's pretty much away from the electric field. The best way to think of flux is how much of the electric field is going through the surface, and in this case you can see that none of the electric field is going through the surface just because it is parallel with the E field, therefore the flux in this case will be 0. And you can even prove this to yourself by evaluating the same equation for the electric flux, which is E times A cosine of phi. In this case, cosine of phi would be cosine of 90, which is equal to 0. Therefore, the rest of the equation would be 0, which thus proves that flux with the surface being parallel with the electric field would be 0. So part C in this case would kind of be the opposite of what part B was asking. It's asking what would happen if the n-hat vector was at a parallel angle with the electric field, meaning that the angle produces an angle of 0 degrees this time. To give you a visual representation of what the n vector is doing, it's pretty much making it so the angle is 0 degrees, therefore the disk is pointing perpendicular to the electric field. Now think about it conceptually. This means that the flux, that all of it is being caught as it travels through the electric field, meaning that the number should be greater than the one from part A, where the angle was at a 30-degree angle, not catching nearly as much flux as it would whenever it is at a 0-degree angle. An analogy I like to use with flux is think of catching fish with a net. Let's say you're holding a net at a 30-degree angle like in part A. You won't catch nearly as much fish as if you hold it at a perpendicular angle to what the river is going through, or whatever you're holding the net at. So in this case, the flux will actually be greater than the one that we found in part A, just because we're doing a cosine of 0-degree angle, which evaluates to 1, as opposed to a fraction of cosine of 30 degrees. And using the same equation that we got from part A and B, E times A cosine of phi, we evaluate E times A which is 2.0 times 10 to the third Newton per Coulomb, times A, which is 0.0314 meters squared, times cosine of 0 degrees, which is 1, and our answer ends up evaluating to 63 newtons times meters squared per Coulomb, which is bigger than the 54 newtons times meters squared per Coulomb that we found in Part A. This completes Part C. Thank you very much for watching, and this completes Exercise 22.1, Electric Flux through a Disk.